Good morning, everyone. We are Team Unicode, and our problem statement is Remote Classroom for Rural Colleges under the theme Smart Education. Now, let me quickly explain the problem faced by students studying in rural colleges. There are three main problems. First one is faculty shortage. No local teachers are available for expert subjects like AI, ERVR, VLSI, or renewable energy in all such fields. Second one is infrastructure gap. Internet connection in rural areas is generally very weak. They are limited to use either 2G or 3G networks. And the third one is device constraints. Most students in rural areas use entry-level smartphones that has very less RAM and very little storage. These are some of the challenges faced. And there are some traditional video platforms like Google Meet, Zoom, or Teams that fail in rural reality because they assume high bandwidth. That is, they require about 500 MB per hour, costing rupees 25 per student. And they also require stable internet connection and high-end smartphones or laptops for them to function properly. These are not available in rural areas. So the students are either forced to self-study or move to cities for coaching. This widens the urban-rural education gap. This is the problem statement. And our solution is a software-only, low-bandwidth virtual classroom environment that is designed to fit the rural realities. And the workflow is as follows. First, the faculty can use either Blackboard mode or PPT mode and can take live classes or can upload pre-recorded lectures. After uploading, the system optimizes it by compressing it. Let us assume they are uploading a video of about an hour, about 500 MB. Then it will be compressed to about 25 MB by using a tool called FFmpeg. Instead of giving it as an hour-long lecture, it is broken down into small parts called mini lessons, each of about 5 to 6 minutes. It is also done by using the tool FFmpeg, and then each mini lesson is converted into audio plus slides alone. Instead of giving it as video, it is broken down into slides by taking screenshots at regular interval, either at regular interval or when the content changes. Depend on the mode, we can take screenshot, and then audio is extracted from the video. So now the video is finally converted into audio plus slides alone by using tool called FFmpeg. After converting it, each mini lesson are bundled into a ZIM format. ZIM format is indexed and it is easy for searching purpose and it is offline ready. Moving on to the student access and features, the student can access in three modes. Live mode, where audio and slides is available and low resolution video can be optionally provided. Offline, where the student can download the video once and can view any number of times. Peer-to-peer mode, where one student can download the video and can share it with the entire class so that one student download can serve the entire class. And other activities like quizzes and polls can be conducted offline, can be attended by student in offline mode. When the internet connection is back or when they are having stable internet connection, the result will be synced entirely. And then we have a dashboard for monitoring all the student activities, faculty activities, quiz results, and all such things. This is our proposed prototype, and it addresses all the problems because the faculty can work remotely from wherever they are without traveling. And our application works in a low bandwidth environment and even in entry-level smartphones. And we also provide offline continuity and peer-to-peer sharing that helps easy accessing of contents. Moving on to the tech stack use. For front-end, we are using React. For back-end, we are using Node and Express. Python scripts are used for automation. And for Android app, we are using Java or Kotlin. As I already said, for processing, for compressing and dividing it into slides, we are using FFmpeg. And for converting into .zim format, we are using OpenZim. And for viewing the ZIM file, we are using Kivix. Kivix is an open source tool that is optimized for viewing ZIM files. And for database, for offline management, we are using SQLite for activities like quizzes, polls, and all such things. And for online activities, we are using PostgreSQLs. And for sharing the data, we are using Bluetooth, USB, or SD card, Wi-Fi Direct, and all such features. Security, for maintaining the security, we are using HTTPS along with AES encryption. And for converting the audio from video into transcripts, we are using OpenAI Whisper. This is the tech stack used. Moving on to feasibility and viability, the video is compressed with FFmpeg from 500 MB to about 25 MB, and it is also storage friendly. Even on entry-level smartphones, it can be stored. Our application can work in a low bandwidth environment, and offline search access is provided by using ZIM format, and it is also sustainable and scalable. There are some risks associated with our application. First time download may fail on unstable networks. Peer-to-peer sharing may face compatibility issue among devices. Teacher adoption could be slow if uploading feels complex. And monitoring and analytics becomes limited when the internet is not reliable. These can be overcome by using resumable downloads. So when a download is interrupted, it can resume automatically when the internet connection becomes stable again. Instead of giving only one sharing option, we are providing multiple sharing options. They can use either Wi-Fi or USB or SD card. Teacher can upload once and system converts it into ZIM. So no technical skills are required from teacher side. An offline first dashboard is also available. Moving on to impact and benefits. First, potential impacts on target audience. Around 250 million students live in rural area, and a study showed that only 24% of government higher education institutes have internet access. So our solution can bridge this gap, giving students access to expert lectures and reducing the urban-rural education divide. And from teacher side, the one-click upload feature lets teacher reach 10 times more number of students than in traditional classroom. So it makes it easier to share the knowledge without any extra effort. And from college side, it can reduce the need to hire adjunct faculty. It saves around 50,000 to 1 lakh per month, depending on the subject. And from government side, uh, a scalable, low-cost, open-source model could save about 8,254 crore on digital education infrastructure and licensing fee that supports government digital education goals. Moving on to benefits of the solution, uh, our platform could provide quality education to the students currently without access to specialized subjects. It also helps build digital literacy among millions of students and teachers, narrowing the existing digital divide. Moving on to economic benefits, student data costs could drop about 90% compared to video platforms like YouTube or Zoom. The government could save up to 8,254 crore on infrastructure and licensing fee. Access to advanced subjects like AI, VLSI, and renewable energy could improve job readiness and employability for the rural youth. It also reduces the travel cost for students and teachers by enabling remote learning. And environmental benefits include reducing intercity travel for coaching by 50 to 70%. It can cut of carbon emissions significantly. Compressed content reduces server storage and bandwidth usage by about 60%, lowering the energy consumption in data sets. We have attached research and reference link for the sources related like Google Meet, Zoom, OpenZIM, QX platform, FFmpeg, and our solution also supports National Education Policy 2020's vision of digital inclusion, and it also complements the plan like Diksha and PM e-Vidya for low-cost learning resources. Now, let me quickly show our proof of concept in action. This script automates everything. We just need to pass the input video and mode. Here we are considering input video example.mp4. It is about 30 minutes long, and this video contains audio, visuals, and slide. Instead of giving it as an entire 30 minutes video, it is divided into 3 videos, each of 10 minutes, by using FFmpeg. And for converting it, this is the code for doing such automation. It compresses, splits, and packages the course into a .zim file, the same offline format that is used by Wikipedia, along with some CSS styles that we have added in this. These are the code that we used. Here we are giving example.mp4 as input and output lesson as output, and we are using slides mode because from video screenshots are taken at regular interval, and here we have given interval as 30. So screenshots are taken for every 30 seconds, and the video is converted into audio and slides alone. Here in output lesson 2, we have the output for this particular video. The 30 minutes video is divided into three chunks, and within each chunk it has slides along with the audio, and it is compressed as .zim file. .zim file is used because it is compressed and it is offline first file format and provides indexing, which is easier. And we are using QX app for viewing it because Givix is optimized for ZIM files and it provides a clean, lightweight interface with built-in keyword search. It is also open source and free, so students did not pay any cost for accessing it. Here, the student can search for the lesson bounded buffer and can view that particular lesson. Here, the student can access particular slide by
We
using
have
next
learned
slide or
earlier
previous slide.
about cooperating processes. As something like the number of items that are placed in the buffer. Different items are being placed. You have the number of items that are buffer is full. The counter is the variable that maintains.
Here we have used a simple lightweight UI where the student can swap between light mode or dark mode at each stage. While viewing video also they can swap between the modes and they can search for particular lesson. So by this process, the entire 30-minute video is converted into 3 videos, each of about 10 minutes. And each 10-minute video consists of slides and audio alone. This is our prototype model. Our solution is innovative, practical, and scalable. It transforms rural classrooms into connected learning hubs without heavy infrastructure, without expensive devices, and without widening the digital divide. We believe this can bring city-level expertise to every rural campus and make quality education a right, not a privilege. Thank you.